We move on to another fundamental concept, which is the concept of field. When we study electric forces, we deal with Coulomb's law if the charges are of negligible dimensions, which we call them point charges. But once you deal with extended objects, then you need to deal with the electric field rather than with Coulomb's law when you study the electric forces. In order to understand the concept of field, we think of the gravitational field of Earth, which we learned in Physics 1. The gravitational field of Earth attracts all objects near the Earth's surface and give them acceleration g 9.8 meter per second squared, right? So the concept of field is not foreign to us. We are familiar with the concept of field from Physics 1. Now, rather than talking about Earth as the source of the field, we talk about charged object like this sphere. This is the source of the field. This is the source of the field. It can act on other charges. If they are of the same type, it will repel them. If they are of different type, it will attract them. So rather than think of direct interaction between charge and charge, we say the charge here, the source charge, produced a field around it, this electric field E, and any other in that field will interact with the field just like masses will interact with the gravitational field of Earth. Okay? So I hope now we understand this concept. In order to define the field, we check on the force per unit charge. If you want the field at this point, imagine that you have a test charge Q naught, then measure the total force between the source and this test charge. The total force, divide that by the test charge Q naught, so you have force per unit charge. This force per unit charge is called the electric field. Okay, the electric field. So from this definition, the unit of the electric field is a unit of force divided by a unit of charge, so it's a Newton per Coulomb. And the direction of the electric field is the same as the direction of force. Usually for source charges that are positive, the field will be going outward, and for negative source charges, the field will be going inward. Okay? For a positive source charge, the field is going outward. For a negative charge, the field is going. Yes, Benjamin.
So for Earth, the negative force or negative, it'd be a negative charge, right? Because we're drawing things in.
You mean the gravitational field of Earth? Yes.
Yeah.
Yes.
Okay.
If you want to apply the same analogy, yes, you can assume that. Yes, the gravitational field of Earth is going inward, so it would be as if Earth has a negative charge. Okay? Yeah. Another point to understand here, we have symmetry. Because of that, we expect the electric field not to be only at this point. We expect the electric field to be coming from all directions inward toward the center of the sphere. And for this one, again, because of symmetry, we expect electric field lines to be going outward radially in all directions, originating from the center of the sphere and going outward. Okay? Because of that, sometimes we call the negative charge a sink and the positive charge a source. A source because as if it's a source of light, it radiates outward. Sink it sucks the field lines inward toward the center. So from the definition of the electric field, F divided by Q, we make the force on any charge now. Simply, it is Q multiplied by E. So now, if Q is positive, then the field is going outward, and the force acting on this charge is Q naught E. If the charge is negative, the source charge is negative, the field is inward like this, and when you have this charge, the force on this charge will be Q naught E, and it is directed inward along this line. Okay? To recap what we learned so far, we learned about Coulomb's law and the law for the electric field. So here, if you take this equation, divide F by Q naught will cancel with the Q naught, and you end up with this definition for the field. It is KQ over R squared. KQ over R squared. Okay? The thing that I want you to understand and to remember always is that the field depends on two things. It depends on Q, the source of the field, and it depends on position. Okay? Depends on the source, the charge of the source, and depends on position. This is very much similar to G, the gravitational field of Earth. G depends on the mass of Earth and on the separation from its center. Imagine you have this situation. Two identical charges, each one is plus Q. So halfway between the two charges, the field will be zero, because this charge will create a field going to the left, and the other charge will get a field going to the right. And because of symmetry, Q is the same as Q, and R in both cases is equal to D. So the two fields are equal in magnitude, opposite in direction. Therefore, the net field is zero. So the electric field is a vector quantity. Like all vector quantities, we use the superposition principle when you add vectors or subtract vectors in order to find the resultant vector, the resultant field. A test charge of 3 microcoulomb is at a point P where the electric field due to other charges is directed to the right and has a magnitude of 4 multiplied by 10 to the power 6 in Newton per coulomb. If the test charge is replaced with a negative 3 microcoulomb charge, the electric field at point P. Now, you have these options. Please read them carefully and help me with an answer.
Would it be 1?
1. So it has the same magnitude as before, but changes directions. What do you think, Victor? You agree with Benjamin?
I'm not sure, but I think I would go with 1 too.
I want you to think further, deeper. The field doesn't care about the charge. Whether it is a plus, whether it is minus, the field is a property of another charge, another system. Right? So the correct answer, it remains the same. You understand that?
Okay.
The field
Yeah.
does not care
It doesn't.
about the charges around it. The field is a property of the source charge. So in this problem, when it tells us that the field has this magnitude and it is directed to the right, this is the field generated by some other system of charges. It doesn't care about the test charge, whether it is a plus 3 or minus 3 or any other value. It doesn't care. It will remain the same. Okay?
Okay.
Thank you. A circular ring of charge of radius b has a total charge q uniformly distributed around it. Choose the magnitude of the electric field at the center of the ring. Think of the symmetry. You have a electric ring. So if you split this ring into tiny slices, for each slice at one side, there is an opposite slice from the other side. Think of the fields due to such opposite slices. Then sum all slices together. What would be the right answer? This would be the right answer. The fields will cancel each other. If you pick any slice, it will have some field, kq over b squared, and from the other side, there is another kq b squared, but opposite in direction. And the same story repeats for all slices at the circumference of the ring, right? So the total field from the symmetry, the total field at the center of the ring will be 0. A free electron and a free proton are placed in an identical electric field. Now, each particle is acted on by equal magnitude electric forces and both have the same magnitude of acceleration. True or false?
I think
want you to recall what you learned in physics 1. Remember Newton's second law? Yes? Any suggestion?
I think it would be true.
True. For this to be true, neutrons and protons need to satisfy two requirements. First, they need to have the same charge, which is okay, and they need to have the same mass, which is not okay. You know that the mass of the proton is like 2,000 times greater than the mass of the electron.
True.
Right? So if you apply Newton's second law, the forces are the same, but the masses are different, so the accelerations will be different.
Okay.
Right? Because they have different masses, the accelerations will be different. Thank you. When you solve problems in electricity, it is always good to sketch the graph for the situation, for the problem. Identify the identity of the charges, which is positive, which is negative. If you are having like microcoulomb, you need to convert that into coulombs. If you have centimeter, you need to convert that into meter. You need to be using SI units all the way. Then you are ready to apply Coulomb's law. Usually, when we solve problems, it is convenient to decompose the forces. If you have multi-charge particle systems, it is convenient to decompose the forces into X and Y components and evaluate the resultant for the X components, the resultant for the Y components, then apply the Pythagorean theorem and trigonometry to determine the final force in magnitude and direction.